Good morning, everybody. Today we are going to start our new topic, that is centrifugal pump. The hydraulic machines which convert the mechanical energy into hydraulic energy are called as pumps. The hydraulic energy in the form of pressure energy. If the mechanical energy is converted into pressure energy by means of centrifugal force acting on the fluid, the hydraulic machine is called as centrifugal pump. Centrifugal pump act as reverse of the flow in the centrifugal pump is in the radial outward direction. The centrifugal pump works on the principle of force vortex flow, which means that when a certain mass of fluid is rotated by an external torque, the rise in pressure head of rotating liquid take place. The rise in the pressure head at any point of rotating liquid is proportional to square of the tangential velocity of the liquid at that point. Thus, at the outlet impeller, where the radius is more, the rise in the pressure head will be more and liquid will be discharged at the outlet with high pressure. Due to this high pressure head, the centrifugal pump, liquid can be lifted to a high level. Now we are going to see the main parts of the centrifugal pump. This is the schematic diagram of the main parts of the centrifugal pump. The first part is impeller. Second part is casing. Third part is suction pipe with footwall and strainer. Fourth part is the delivery pipe with delivery wall. Now we will concentrate on the first part, that is impeller. The rotating part of the centrifugal pump is called as impeller. It consists of series of backward curved vanes. The impeller is mounted on a shaft which is connected to the shaft of the electric motor. Now, the second part of the centrifugal pump is casing. This is the casing. The casing of the centrifugal pump is similar to the casing of the reaction turbine. It is an airtight passage surrounding the impeller and is designed in such a way that kinetic energy of the water discharged at the outlet of the impeller is converted into pressure energy before water leaves the casing and enters the delivery pipe. This type of casing is called as volute casing, which surrounds the impeller. It is a spiral type in which area of flow increases gradually. The increase in the area of flow, as the increase in the area of flow decreases the velocity of flow, and decrease in the velocity increases the pressure of water flowing through the casing. Then we will see the next component of centrifugal pump, that is suction pipe with a footwall and strainer. A pipe whose one end is connected to the inlet of the pump and other end dips into the water in a sump is known as suction pipe. A footwall, which is a non-written wall. A footwall, which is a non-written wall or one-way type of wall, is fitted at the lower end of the suction pipe. The footwall opens in upward direction only. A strainer is also fitted at the lower end of the suction pipe. Now, the last part or the last component of centrifugal pump is delivery valve or delivery pipe. A pipe whose one end is connected to the outlet of pump and other end delivers the water at the required height is known as delivery pipe. So it was about the components of the centrifugal pump. Now we are going to see work done by the centrifugal pump on the water. For this, we will require inlet and outlet velocity. In case of centrifugal pump, work is done by the impeller on the water. The water enters the impeller radially at the inlet, which means the absolute velocity of the water at inlet makes an angle of 90 degree with the direction of motion of the impeller at inlet. Hence the angle alpha is equal to 90 degree and whirl velocity at inlet is equal to 0. For drawing the velocity triangle, we are going to use the same notation that we have used in case of the turbines. Then this is the blade. Angle alpha, angle theta, tangential velocity u1, absolute velocity v1, relative velocity vr1. Now we will draw outlet velocity triangle. This is relative velocity at outlet. This is angle phi. This is flow velocity at outlet Vf2. This is absolute velocity at the outlet. This angle is beta. Now this component is whirl velocity at outlet and this whole component is equal to tangential velocity at outlet. Now N is equal to speed of the impeller in RPM. Speed in RPM. D1 diameter of impeller at inlet. Diameter of impeller at inlet. Then U1 is equal to tangential velocity of impeller at the inlet. The formula is pi d1n divided by 60. Pi d1n divided by 60. Now d2 is equal to diameter of impeller at the outlet. U2 is equal to tangential velocity of impeller at the outlet. Then U2 is denoted by the formula pi d2n divided by 60. As you know, V1 is the absolute velocity of water at the inlet. VR1 is equal to relative velocity of the water at the inlet. alpha is equal to angle made by the absolute velocity at inlet with the direction of motion of the vane, and theta is equal to angle made by the relative velocity at the inlet with the direction of motion of the vane, and V2, VR2, beta and alpha, the corresponding values at the outlet. Now, as the water enters the impeller radially, which means that absolute velocity of the water at the inlet is in the radial direction, hence angle alpha is equal to 90 degree and bulk velocity at inlet is equal to 0. A centrifugal pump is the reverse of radially inward flow reaction on the runner per second per unit weight of the water striking per second, that is the in case of radially inward flow reaction turbine, radially inward flow reaction turbine, the work done is 1 by G into bracket VW1 U1 minus VW2 U2. We have seen this. Then work done on the impeller by the impeller on the water per second per unit weight of the water striking per second. That is, in case of centrifugal pump, this work done will be equal to minus work done in case of turbine. When this will happen? For the work done in centrifugal pump. Okay. Therefore, minus 1 divided by G VW1 U1 minus VW2 U2. That's why it become as 1 divided by G into bracket VW2 U2 minus VW1 U1. But as VW1 component is equal to 0, it will become as 1 divided by G VW2 into U2. Now, if we consider weight of water, that means work done by impeller on water per second, that will be equal to W divided by G into VW2 into U2, where W is equal to weight of water, and that is equal to rho into G into Q, where Q is equal to volume of water and formula for Q is equal to area into velocity of flow, that is equal to pi d1 b1 into vf1, that is equal to pi d2 b2 into vf2. Okay, where b1 and b2 are the width of the impeller at the inlet and the outlet, vf1 and vf2 are the velocities of flow at the inlet and the outlet. This equation 1 divided by G VW to U2, that is work done by the impeller on the water per second per unit weight of water striking per second is gives us head imparted to the water by the impeller or energy given by impeller to the water per unit weight per second. Okay, here we will end our lecture. Thank you.